Sorry? Oh.
You want to give my talk?
Hope I didn't say anything.
Good.
Okay, so next we have Larry Brown, and his title is up. I don't know that I can pronounce it. So.
Heteroscedastic? That's the one, yeah, that just means many variances. That one you can say that way. Thank you, Ingrid. There's my title. Actually, even before I go to the first slide, let me kind of point out that this requires a little bit of shifting of gears here. High dimensions to me means anything more than 2. And this is very high. What I'm thinking about are statistical problems with dimensions in the tens, hundreds, or thousands, but not millions. What we might learn here is useful in its own right and may have messages, sometimes does have messages for problems that are orders of magnitudes larger, and sometimes has messages that aren't necessarily worthwhile. I'm not trying to sort that issue out today. I want to talk within the framework of problems that have hundreds or maybe thousands of unknown means, and for which, or perhaps more, but for which the sparsity is more than the order of magnitude that Ingrid and most of you have been talking about. These kinds of procedures are calibrated more for situations where the sparsity might be a small power of n, but probably not log n. So think of a normal location problem. So it's a simple canonical problem. Observe normal variables with an unknown mean and known variances, but do not make the assumption that the variances are equal. They may be unequal, and that, of course, is the point of new work. There's a tremendous amount of literature about the homoscedastic problem. There's much to learn yet about that problem, but much less thought about heteroscedastic cases, even though much of what happens in the real world, maybe all of it, is really heteroscedastic. The goal is to estimate theta, the classic goal, by theta hat, and I want to measure the quality of the estimation procedure by ordinary squared error loss, though for asymptotic purposes I'm going to norm that to take the average, so it's average squared error loss. Lots of generalizations are of interest, some of which we've looked at, but I'm going to stick today to this, this simple setting. Here's an example. It's easy to focus on, easy to think about. There are, of course, much more important examples out in the world, but the data here is easy to conceive and has taught us quite a bit about such problems. Look at the batting average of major leaguers for the first half of 2005. Doesn't matter. Here we don't have to talk about baseball. I can give this talk to a baseball audience and spend the whole hour talking about batting stances, whatever you will. So the model here is that you observe variables Ri. There's about 500 and some of them in this data set that are binomial, Ni, Pi. Ni is known, Pi is not. The objective is to estimate the P's. That's a binomial problem. It can be considered in that way in its own right, but much more is known about Gaussian problems, and those are the ones I want to talk about. So we make a transformation. and let our xi's be the arc sine of the sample proportions, adjusted slightly. The adjustment is helpful. The quarter and half, as discussed in an earlier paper that's appeared a few years ago in the Annals of Applied Statistics. The adjustment pretty much guarantees that this xi is really very close, for all practical purposes, to normal as soon as ni is about 10. And so we limit our data set to batters that have appeared at least more than 10 times in the first half of the season, saving the second half for validation. We observe xi's that are normal, mean theta I, very close to normal, and a variance 1 over 4 ni. And note that here, unlike most real-life problems, the variances are actually known. In most cases, they need to be estimated. The procedures that I'm going to talk about can be modified to situations like that. But here is a pure case where the variances are actually known. And we're trying to estimate theta I, which is the arc sine square root of pi. Again, the quarter and half don't appear in the inverse transformation. That's the key to the trick. Use xi to estimate theta I under mean squared error loss. Think of a classic empirical Bayes way of approaching this problem. This kind of reasoning goes back, well, it goes back to Charles Stein in 1962. And was considerably developed by Efron and Morris in the 70s and referred to in some earlier talks in this session. It's still the way to go to understand it's the direction to move. Think of x, so the xi's are normal with known variances. Think of the theta i's as having a distribution g lambda. In this case, lambda is the variance. For convenience, I use lambda, not lambda squared. Lambda is the variance of the normal hyperprior on theta. Here I write normal 0 lambda. We'll generalize a little in the next couple of slides. The Bayes estimate given lambda is just the posterior mean. An empirical Bayes estimator in philosophy is derived by estimating lambda somehow from the sample and then plugging into the Bayes formula. So what makes it empirical Bayes is that estimation step of the hyperparameter. How that's done has a lot to do with how well the procedure works or does not work. Of course, it works much better if the hierarchical structure is nearly correct as well. In a full Bayes hierarchy, lambda would be distributed according to H, where H was assumed known. So the other tool, or the tool that I want to bring in, is Stein's unbiased risk estimate, which first appeared in a paper in the early 70s by Charles in a kind of obscure place, but was quickly brought into standard usage. For an estimator that I can write as xi plus xi, so xi is just the difference between the estimator and x, the risk turns out to be the expected value of this quantity that has come to be called SURE, Stein's unbiased risk estimate. It's kind of awkward English, but it's a good acronym. And there's the expression up on the board for SURE. It's not important really to absorb the expression at this moment. It's an unbiased estimate in the sense that its expectation is the quantity we want, and it has no parameters in it. Sigma I squares are known. And it's fairly simple to write down. It does require derivatives of xi, partial derivatives, but here we're working in an explicit context where that's not an issue. The conjugate prior Bayes estimator, from the previous page. It's just a linear estimator in X. And so Sure has a very simple form. And again, it's not really important for you to sort of internalize what that form is. I write it mainly to show you that it's very simple. There are other ways to derive this same procedure that actually have a slightly about the same length history. Because it's a linear estimator, this is also what's called Mallow's CP. So the Sure estimator is the estimator that one derives by looking at that. Let me go back at this unbiased estimate of the risk. You look at that. You differentiate it with respect to lambda, set the derivative equal to 0, and so you find the best lambda, the arg-min of Sure, and you plug that back in. So in that sense, lambda hat is your empirical Bayes estimate of the or is your estimate of the hyperprior from the data, but it's not really an estimate that you necessarily think is a good estimate in its own right. It's an estimate that you think will perform well to get you a good risk, and it does. Just for comparison, there are other estimators that have been proposed, that have been used, and that I'll look at numerically in a few minutes. You can use maximum likelihood to estimate lambda, and that's equivalent to a slightly different equation. Or you can use method of moments to estimate lambda. There are more than one way to do it, but the standard way, or the way that we like, would involve solving the equation at the bottom. So they are different equations. The main point here is that the equations are simple and that they're different. So you get different estimators depending on different approaches, method of moments, maximum likelihood, or now the Sure approach. In the homoscedastic case, really as a parenthetical comment, if all the variances are known, then all three of those estimators, all three of those estimation equations turn out to be the same. And what you get out of the approach is an estimator, a shrinkage estimator that looks like the James Stein estimator. I really wish I had a pointer, so I'll use my finger. You get a p as the multiplier up in the numerator there, instead of the p minus 2 that comes from the Stein estimator, or that's traditional in the Stein estimator. The p minus 2, it can be argued, in some sense is a little better, but the p results from sort of the lack of specificity, or some of the approximation that happens in the, it didn't work for some other people. Is it going to work for me? Do I see it? Yes, there. So there's the p minus 2, there's the p. So this all has to do with a little bit of the fact that the Sure estimation logic has an approximation step in it, and that's where that 2 comes from. I've also put a positive part on these estimators. Some of them naturally come that way. The maximum likelihood estimator naturally comes with the positive part. So does the Sure estimator, for that matter. The method of moments estimator doesn't naturally have a positive part, and so I've modified it. It makes no sense in any way not to put the positive part in there, so I've done it. There's another estimator that you may be familiar with, some of you, called Sure Shrink, that Donahoe and Johnstone used in a wavelet setting that can be reduced to something that's essentially the same estimation problem, homoscedastic. And in our context, or thought about in our language, it uses this soft threshold estimator there. That's a soft threshold estimator, and chooses the threshold or the constant in that estimator to minimize Sure among all such soft thresholded estimators. And then there's a little truncation step, which makes it work better in the context that it's intended for. This can be thought of as the regularized estimator for an L1 penalty, and also the empirical Bayes posterior mode under a Laplace prior with scale, with this as the scale. So it is also a kind of empirical Bayes estimator, although it involves a posterior mode instead of a posterior mean. So that's the basic methodology I've already mentioned it, is the Schur estimator that we've derived, built from the standard conjugate prior structure. It works better if you put a mean. Put a mean in there. Theta I is given lambda is normal mean mu and variance lambda, one mean. That's an extra hyperparameter. That makes the estimator work better. We understand that. So did James and Stein, and definitely Effron and Morris in their series of papers. So there are two possible ways to go from here. We need to estimate both hyperparameters mu and lambda. One thing to do is to plug in an estimate of mu x bar. Plug in x bar as an estimate of mu, and then use Schur to derive the estimate of lambda. And another way is simply to use Schur all the way through. This seems to me a more pure logic. Minimize over both mu and lambda. But there are two different estimators, and they actually perform a little differently in our simulations and on the data set, on the baseball data. A nice generalization, in fact, in some sense, the only really new story here is the fact that this whole logical procedure can be carried out even in a much less structured way. Let's go back to the complete hierarchy, the hierarchical Bayes setting. Just doesn't work. Here. To the hierarchical Bayes setting here. And instead of assuming that lambda is fixed, let's think of that didn't work. Instead of thinking of lambda as fixed, but unknown, think of the more complete Bayes structure in which lambda is distributed according to h. Then one gets the Bayes procedure involves the expectation over h of lambda over sigma square plus lambda given x. And for a broad class of hyperpriors, it turns out that beta is monotone in sigma I squared for each x. It turns out that way, so let us impose just that restriction on the multipliers beta in this formula and minimize Schur over the class of all monotone estimators. Monotone in sigma I squared for fixed x. There's the estimator. That's the formula. And I just note, I keep hitting something that's... And I just note that one can prove that if G, it's actually H, that's a typo, has a log concave density, then beta hat is in monotone. So we're talking about a class of estimators that includes anything in this hierarchical structure where H has a log concave density. And in particular, Donahoe and Johnstone's Schur shrink, even though it's not a posterior mean, that soft threshold estimator also satisfies this condition. So that when we calculate theta hat, when we calculate the monotone estimator, monotone sure shrink estimator, we should be improving on sure shrink, at least for sufficiently large sample sizes. We have a series of asymptotic, a collection of asymptotic theorems, one for every one of our estimators. Details of the proofs are partly similar and partly require looking at the specific structure of the estimators. All of the estimators are asymptotically optimal in a quite strong sense. Actually, they do as well as let me do it this way, they do as well as an oracle here, an oracle that actually knows theta and wants to minimize the posterior loss, knowing the truth, but within the class of allowed estimators. So we do as well as those asymptotically in the sense of squared error, or average squared error. So let's look at the baseball data to see how well this performs, and I'll close with a couple of simulations and a concluding comment. All the empirical Bayes estimators, I've changed the form a little. I've also lost the back of... all of the empirical Bayes estimators can be rewritten in this form. It fits the baseball context. Ni is the number of at-bats. Gamma, if gamma is 1, then you believe their existing average as your estimate. If gamma is 0, it means you've reverted to the overall mean. All of the values of mu hat for all of the estimators are all pretty similar, and so the only thing to note is that they're not all the same. They do differ, and one of them, for reasons that I don't quite understand, is rather different. The true sure estimator, where you estimate both hyperparameters on the basis of sure. The gammas do look different. So the amounts of shrinkage, this is really the reverse. When gamma is small, you're doing a lot of shrinkage. You're not relying on the published baseball records. You're relying on the overall mean. The amount of shrinkage, 1 minus gamma, varies a lot among these estimators. It's, of course, all increasing. The amount of shrinkage is decreasing with the number of at-bats. The more a player has, the more data you have, the more you rely on the data. And the other thing to note is that the monotone estimator moves up in steps, which you will know as the solution to that restricted minimization problem, and it's what the function you're minimizing is easy, and it's a monotone minimization, so that whole story is easy, especially for samples of the size we're looking at. The relative risks are interesting, and except for the sure estimators, I'd seen this table before in my earlier paper. Look at just the first column of all batters. These are the relative risks, our estimate of the relative risks with the risk estimated from the second holdout sample. That's not a predictive risk, it's the actual, it's an estimate of the risk as an estimate of theta in this case. And it's been normalized so that the naive estimator, which is what the baseball fan usually does, looks in the newspaper, sees my batter, my favorite batter on my dream team is batting .310 for up to now, so I think he'll bat .310 for the rest of the season. That's the naive estimator. We've normalized these numbers so they're 1. Turns out that just using after half a season, just using the grand mean is better than reading the newspaper. Well, we all knew that reading the newspaper was kind of a useless enterprise anyway. And after half a season, that's what it is if that's how you're going to use the newspaper. But if you apply any one of the other shrinkage estimators, you do better. In this case, the big surprise was that the maximum likelihood estimator worked very bad. Only 1 minute? I'll talk only about the baseball data and not about simulations, which is fine. The Sure estimators work well, better than the estimators that we had before, which were the pure empirical Bayes. And the best estimators are the monotone ones, which is the new thing. That's not really a surprise. We're minimizing over a larger class of estimators. So with enough data, the asymptotic said we should do better. This is enough data, and what's really going on here is that this data does not exactly satisfy the assumptions we set out before, but because the minimization problems here don't require the assumptions to be satisfied, they only require us to be using a good class of estimators, because we're doing the best among the class. So that's the main story. There's the plot. I was going to talk a little bit about this plot. There's the badly performing maximum likelihood estimator. It shrinks way too much. There's the best estimator, the monotone one, this light blue. Fortunately, it's light blue, but note it kind of turns up. For batters that bat a small amount, it shrinks a noticeable amount. For batters that bat enough, it begins to turn up so that you can read the newspaper. If your player is a regular, bats 320 over half a season, has lots of at-bats, that's probably pretty good information. Well, that's basically the story. Those are simulations. In summary, we have a possibly heteroscedastic model. You consider a family of estimators, theta hat of lambda with some parameter, a lambda, although it can be also kind of semi-parametric. You write the Sure estimate of the risk for fixed lambda. You minimize this over that family. Then it turns out that the estimator has desirable asymptotic properties, at least that depends on the class, but all the classes we've considered that work, very desirable within the context we're working, and it performs well in practical examples and simulations. The class is the class of estimators that are prescribed. So in the first case, they're linear estimators of the form lambda over sigma I squared plus lambda. In the last case, they're simply monotone estimators with monotone multipliers. So you take the class of estimators that you're using, and the oracle is the oracle within that class. And that's how well we're doing. So whether this is useful in a broader context depends upon whether that oracle attains the target that you want.
Other question? Yes?
Have you also looked into modeling sigma I?
Yes.
Repeat the question.
Have we also looked into modeling sigma I squared? Yes. There are various scenarios, and we've looked at some of them, where you have estimates of the sigma I squares. They can be independent on each coordinate, or it can come from an array where there's only one unknown scale, and that situation we understand well, or almost as well as this, but some others we don't understand as well.